after a short break. Now I'm together with Jacek Karolczak, who is a deep learning engineer at nCodex, and Jacek will tell for us about unlocking the potential of large language models and enhancing chatbots with GPU-centric vector databases. As always, you can post your question to Jacek's presentation on the chat. And Jacek, let's make your show.
Thank you. Thank you for the invitation to speak in such great venue. Thank you for a great invitation, and thank you for coming to my presentation. I hope you will enjoy it. Here you can see the agenda of today's speech. I will start with short introduction, maybe a reminder for you about prompt engineering. Then I will say about vector stores. I will extend this to vector databases. Finally, I will show a few examples how it works in practice, and then will be a summary and time for your questions. So it's 2023 and it's machine learning related conference, so I feel almost obliged to mention something about LLMs. So here's an example that LLMs are great, right? You can ask them arbitrary question and they will always give you an answer. Usually the answer will be correct, even if it's about some numbers like dimensions of Jaguar. And I didn't spot it before, but they answer correctly, even if I have a misspell of the word in the question. So they are great, right? Yeah, and they are great, but only sometimes. Because, for instance, if I ask about the height of Jaguar, the question may have a few correct answers, because Jaguar can be a cat, but it also can be a car producer, or maybe a roller coaster in California, or I didn't put it in slides because I found it too late, but there's also a plane that it's called Jaguar. So depending on the context, some answers may be correct, some answers may be incorrect. And if I create a chatbot for a Jaguar, let's say, car manufacturer, then I would expect that the chatbot will give the answer about the car, maybe some specific model, not about the cats. So here is a problem. We know the problem. Here is an idea how to fix it, how to make large language models doing better. So the general idea is to add a context or maybe some additional information that the model may not be aware of. For instance, if you create a chatbot for your company and you are doing some, I don't know, something very specific, maybe something confidential that it's not published publicly, like you have a private API that you share the documentation to your customers after they purchase something, and then you didn't publish this document, so the chatbot, even if it would scrub the entire internet, the company during creating such a chatbot, they wouldn't be able to get the data because it wasn't publicly published. So we can always add some documentations, pages or additional documents to the prompt, and therefore the chatbot will give a correct answer with some specific information. And all of that is part of prompt engineering, which is a much broader term, which relates also to customizing how the model should act. For instance, if it should give the answer as an assistant or maybe as a medieval prince. And here is an example of a prompt that we found in nCodex that worked quite well. I mean, it's pretty simple, but it worked quite well in one specific use case. So as nCodex, we are a startup that has its origins in another startup named Brightlight. So the first project we did to prove that what we are doing makes sense was creating a chatbot for that second company, for Brightlight. So here is a prompt that worked quite well there. So it's pretty simple. What you can spot, it's written here in Python-like f-string notation. So we start with giving the context of the conversation, why it's happening, and what we do, we add some sources that gives a specific information for the given question. So for instance, here we can spot that the question is who is the founder of Brightlight, and we found that these documents are quite accurate. And that sounds great, right? Because the chatbot now, with knowing the sources, knows everything what it should know to give the correct answer. And the question, the real problem that has to be solved is how to find useful documents, because it's quite difficult to compare texts, right? And it's also hard to compare shapes, because shapes, I don't know which shape is the most similar for you to the query with the blue file-like shape. And it's pretty difficult to compare them, but once we are able to transform shapes to the numbers, to vectors, it's pretty simple, because we don't have to compare shapes and their properties. We only have to compute some distances between many instances in this vector space where we have embedded our shape. And we can do the same with documents. And yeah, it's 2023, so probably I shouldn't be talk a lot about encoder and decoder architectures. So the idea is that if we have an encoder for a text, we are able to create a vector that can be easily searched for relevant documents. And to define a relevant document, sometimes it's enough to just encode the question and put to a vector store to find documents. I mean, for instance, API documents that are the closest to the question, because properties that are guaranteed by modern encoders are good enough to solve the question. And here you can spot that the decoder is also mentioned, but actually we don't have to put the decoder. If we are able to store the text, it's much simpler, even better, probably faster, much faster, and the process is much simpler. The decoder actually is only needed to train the model, the encoder, in most use cases. And of course, this scheme is general, works on multimodal, on different modalities of data, for instance, on text, but you can use the same scheme for instance, images like MNIST data set or shapes, what we've shown already. Another difficulty is one difficulty in this searching for relevant stuff is to define the similarity between neighbors. Similarity or distance, because we can always do the trick to do 1- and maximize or minimize the distance or similarity. And depending on the application, many distances can be used. But actually, nowadays, I think like the first, okay, maybe not the first, but some like L2 cosine inner products are the most often used example measures in real-world applications. But there is a great initiative which is named Rapid. It's an open initiative for using NVIDIA GPUs for different things. And this initiative output is, or are many Python or C++ libraries. Probably the most known are QDF, QDAL data frames, or QPy. But there's also Raft, which is reusable accelerated functions and tools for vector search and more, which is an implementation of all these measures, and it's pretty easy. Maybe not that easy, but they're implemented so you can use them. And as you can see, and not only the most popular one are implemented, but also some, for instance, from information theory, like Kullback-Leibler divergence or the entropy. So you can always think about non-obvious use cases as chatbot, as I said earlier. But maybe if you are interested in quantum machine learning and you would like to compare some qubit states after to have a lookup table, then you can think about Draft as a solution for that. Once we have defined the measure, how do we define similar documents, it's still one big problem, because you have to query the database to find relevant documents closest, nearest neighbors. And this can be done by just multiplying matrices, because even I visualized it in such a way that if you have a matrix where row is regards one instance, one document, and you have a query, you can just multiply them and have a array of distances, and then you take the minimum distance and you have the relevant document. And that's great for GPUs, as GPUs are great in computing things on the matrices, and especially if they are floating point numbers, and encoders usually output floating points. And here's the thing that probably is arguable for many people, that okay, that's great that we can do things efficiently on GPU, but it's extremely costly. GPU costs a lot, it uses a lot of power, and you have to, there's no point to using GPUs for such stuff. But it occurs that GPU are actually quite cheap as long as you utilize them on 100%. Here we can see that I compare a 101 Xeon CPU, which cost some time ago roughly the same. And when they are utilized in 100%, then using GPU is way more cheaper in terms of both energy and money. But as I already said, it's always a problem with money, that we have to have money to do something, and therefore running exact search on large document bases, it can be quite costly. So an approximate nearest neighbors problem were defined to not find always the closest documents, the nearest neighbors, to have a guarantee of that, but we can just find documents that are quite close to our query without a guarantee. And therefore, some time ago, many structures dedicated for that, like IVF or IVF-PQ or HNSW, if you're interested in indexes, probably you've heard that names were proposed, but they are great for CPU, not that great for GPU, and therefore they are also not that fast. And much more modern approaches are based on graphs, which are applied to the efficient nearest neighbor search, and they are pre-computed before running query. We build the graph that we use to find nearest neighbors. And the simplest idea that actually most modern approaches are based on is NN descent. It works this way, that we select a random point at the beginning, and then we check its neighborhood, whether it's closer to the our query than our current node. And this way we traverse the graph entirely. We always evaluate the neighbors, select the k nearest neighbors, and therefore we are able to find the final solution. And here, or maybe one more thing, just to mention that it utilizes the principle that neighbor of my neighbor is very likely to be my neighbor as well. Yeah, and here it wasn't very spectacular, very impressive, because I shown an example on small scale. Here you can see the same algorithm working in much more scale. We have a query somewhere here, and we have we start in the worst possible point to searching the graph. And even in such a bad initialization, we can spot that the algorithm is doing great. It just uses, it just searches maybe 10% of the graph of the entire vector space. So we have an extreme improvement here. But constructing such a graph may be quite difficult task for you if you are not aware how it can be done efficiently. So you don't have to remember any further point of this algorithm, further step, because to create a graph for an descent, you can just use an descent on random graph. So you randomly initialize the graph using the k, which is the desired number of neighbors of each document, and then you run one iteration, and after even third iteration, it's almost 100%. So it's pretty efficient constructing such graph. It's not that difficult. And there are even more complex algorithms. I won't elaborate on it more because I heard that in this venue it's expected to do the meet to hear about some applications. So I would like only to mention that there are algorithms that are dedicated for GPUs that are designed by the hardware implementation of GPUs. So for instance, Kagra is an algorithm that is based on NNN descent, but is optimized to use 32 operations at one time, which is a warp size. So even if you would like to multiply two numbers of on GPU, you will do the operation on a warp. So it's like cost of doing 1 or 32 operations is the same. And the algorithm is like up to 77 times faster than NNN descent in some applications. And what I told you is searching the graph. So it's like a vector store. We have a representation of our encodings relating to our documents, and we can find easily relevant documents. And they have a lot of limitations, such algorithm constructions, implementations, even implementations in some modern languages. So one of them is that once you have to input a new document, for instance, you added a class to your API now, or endpoint to your API, and now you share new documentation, you would like to enhance the chatbot with the knowledge of your new endpoint, and it occurs that you have to rebuild the entire graph because there most often are not, it's not possible to just add a single instance, single vector. As there are only libraries, algorithms implemented in some languages, they don't provide data persistence, they just operate in memory. They are difficult to deploy and are accessible only through some very often very specific API. And they don't serve restricting to the vector subspace. And here we are back in our world of shapes where we are looking for similar shapes. We know that we can just encode them and search the numbers, and it's great, but most algorithms works as long as we consider the entire space, the entire graph. Once you would like to consider only green shapes, the algorithm get lost, don't want what to do, it just can search the entire space. So yeah, here I put that nCodex is all you need, but actually database is all you need, because we would like to have, for instance, the data persistence or much more desired features. So once we knew that vector stores works, they're doing great, we started doing enhancing with additional features. We started with the thing that was, for instance, for us the most important So we decided to add some attributes. Usually they are called in different implementations of vector databases metadata, but actually it doesn't have to be metadata. It can be data of arbitrary type. For instance, you would like to have a simple program that you just put a vector to a function, and the function returns the text of the original text document, and that's what can be an additional attribute. You can also would like to limit the vector space, as I shown on example before, just to create to return documents for one specific branch of your company, because you would like to have a different chatbot for different branch. Also, create, read, update, and delete operations are not implemented in vector store. They are typical for databases, serverless GPU deployment, and related to that user interface are also not provided in vector stores. And probably the most important is data persistence, so we don't have to deal with some containers that will restore data after failure and so on. You can just delegate this thing to vector database, and this is the same like having a dictionary in Python and having a Postgres database. Is the same comparison as vector store to vector database. We developed a simple Python API that utilizes the object-oriented principles in Python, and I say we as nCodex, but actually I don't want to advertise that we are the best and the only solution. You can search for other vector databases and you will see similar stuff there, that they provide similar features. Yeah, maybe a bit slower. End-to-end example is pretty short, that if you would like to implement it using vector store, it would be twice of or even thrice as long, even to just search for input and search for vectors in the vector store. And now I hope the most interesting part for you is the question whether it really works, whether it makes sense to build a vector database, to encode some documents and put them to the chatbot to get accurate answers. And therefore, I'd like to present 3 questions. On each slide, there will be next question that we ask to 2 models. First, we ask the question that you can spot in the leftmost column. And so we took a question like, what is bright light? And asked the question to the Alpaca 7 billion implementation. You may ask why we decided to use this model. The reason is very simple. It was able to be put on our machine in our office. And we got some answer that was totally not correct. It's about automated emails and messages. We never did such thing. Then we asked the same question to GPT 3.5, so to ChatGPT, and it occurred that it was doing much better, but it's much bigger model that cost much more. And then we asked the same question to Alpaca, the same model that failed in the first iteration, but now we added some sources. So we performed the scheme presented earlier, that we show part of some document, and we wish that the model will perform better. And it occurred that actually it did much, much better, and the answer was correct. And this is the same model. The only thing that changed was prompt. Another example can be spotted here. It's quite a fun example because the Alpaca without the prompt give an answer about the founder of Brightlight, that was not correct at all. Both first name and last name are incorrect. Then GPT answered almost correctly, but only in a half, because the name is Richard indeed, but it's not Feynman. It's Richard Hynes, so the last answer is correct in 100%. Both first name and last name was good, so you can see the progress here. And the last question was probably the most difficult, because you can also spot different types of questions here. The first one was quite general, what Brightlight is in general. So if the chatbot is aware of some wide context, it should be able to answer the question. The second question was about the name, so very specific information, but the knowledge is not so technical. And the third question is about very technical thing, to answer whether you need a server to use Brightlight DB, which is GPU accelerated database. And Alpaca said that no, you can. So the answer is almost correct, but the reason of this answer is not correct at all, because it says that you can run a local this on local machine, which may be the case if you would really like to, but it's not the default scheme. The second answer by GPT was not correct as well, but the Alpaca enhanced with a few documents which were found using a vector database is completely correct. Everything is correct in this answer. And you can spot that I did something tricky in this presentation. I didn't said even once that you can fine-tune a model. And I did it on purpose, and not because I don't believe that fine-tuning is something good, because I think it's great. But even on the OpenAI website, on the page where it's introduced why it's important to fine-tune model, why it's useful to fine-tune model, and when to do it, with 2 over 3 bullet points that you can see here. So it's just an introduction to the document, say about prompting, that prompt engineering is necessary even if you would like to fine-tune model. The first reason for that is that it might be enough to just give the prompt. You don't have to fine-tune model, which is quite costly. And the second reason is that even if you fine-tune model, it will perform very likely much better using a proper prompt, and just with the hope that it will work itself better. And there are much more applications of vector databases. One of them is email trash, which is a really application that we are aware of as a company, because our partner uses vector database for that. Another idea is some technical support. So if you use Jira and you have it come integrated with Confluence, you can search both for tickets and for documents, or when you write something, it may propose some Confluence pages. You can use it this way by applying vector database. So intelligent chatbots, I already said about it. You can do efficient text search in vast amount of data, and of course you can use it for multimodal data, not only for text. And as I said earlier, probably in some quantum machine learning, there would be an application for that too. Yeah, I was asked to put a QR code to assess my performance, where you can go. Here is the link. Probably there is somewhere in the application as well. So please assess it. I'm open to all remarks about my presentation. And this is the end. Thank you very much for your attendance. And if you have any question, you can reach me out. Here is my email jacek.karolczak@ncodex.io. And that's all. Thank you. Now I'm open. I think we have 5 minutes to answer some questions.
Okay, thank you very much, Jacek, for your magnificent presentation. And now we are starting Q&A session. And I see the first question from Piotr on the chat. If you have long documents, do you paste entire documents, which are the nearest neighbors, into the prompt, or is there a method to clip only the relevant parts of document and only paste those into the prompt?
Okay, so when you have a long document, there's no point to put the entire document. It's much better to cut it to smaller pieces that are overlapping. So for instance, let's do a simplification that we have many sentences, each of size 5 words. So if you would like to have pieces of text in your database that are at most 20 words, what you could do would be to take as the first chunk, first 4 sentences, then overlap a bit the second chunk. So for instance, instead of starting for the 5th sentence, you can start with the 4th one. And actually, you don't have to stick to sentences. You can chunk sentences in half, and that will be great enough for chatbots as well, because what's important here to remember is not to have a text that looks great for human. It's good to have, it's a necessity to have a text that will be informative for chatbot, and the chatbot will transform the text in such a way that it will be human friendly.
Okay, and I don't see any other question, but maybe let's wait a minute for the next one. And if there wouldn't be any other, we'll finish this this slot. And I see from the Adam, how many nearest chunks would you paste into the prompt? Is there any method or golden rule for this?
No, I think there's no golden rule, but it shouldn't be a big number. It should be like 3, 5 documents at most, I think, because you have to remember that inference of large language model is costly and costs a bit, and therefore you don't want to create bigger prompt, which makes the answer also the inference cost more. So I think it's good to experiment, but if you find out that you have to go over 5 documents, probably you can try to deal with different measures of finding a similarity, of defining similarity between documents, because it might be the issue that you selected a wrong measure, wrong distance, and therefore you don't pass really relevant documents, and by refining the measure, the similarity measure, you can get better results.
Okay, and another question from Piotr, but different Piotr. Does the performance degrade with the increasing amount of prompt pieces?
I'm not sure whether the question relates to a large language model or to the vector database. If it relates to vector database, it does, but it's a really small degradation. It's, as I shown on this slide with big graph search, the degradation is like 1/10 of pieces, for instance, in case of such graph that we had there, not that one piece. It's a big degradation. It's very, very small, less than linear. And in case of large language models, of course, it's a degradation.
Okay, and the last question to you, Jacek. Dominic wants to know if some metadata or context summary should be added to each chunk.
it depends on the application. I think that it's not necessary. You can just put a text to a database and related vector and do vector search and just return the text. But sometimes, for instance, if you would like to give the exact document, link to exact document, because you want to have a really reliable chatbot that will prove his answer, but by giving links to documents on which he based its answer, then it's better to add such metadata.
Okay, so Jacek, thank you very much for your presentation once again. Thank you all of you for participating in this session, and as always, do not forget to rate Jacek's presentation using the QR code that Jacek shown or the stars under the video player which you can see. So thank you very much and see you later after the break.